It's fast.
Okay, L'Hopital's rule. L'Hopital's rule says the limit, really it says if limit is indeterminate. Do you guys remember what indeterminate meant?
Can you remind us just in case?
Often it was 0 over 0 or infinity over infinity. You can occasionally, sometimes this is like 1 over 0, might show up in here. Most of the time those do not exist, but occasionally this becomes a thing. And this always involves something as in the form of ratios. If it doesn't involve something in the form of ratios, you need to make it into the form of ratios. But most of the time it does. Most of the time we have problems with limits when they're something over 0, right? So we'll deal with some. This might take attendance. And I actually did it. So what this says is the limit is going to be the same if you take the derivative of the top and the derivative of bottom. No quotient rules. Take the derivative separately.
No, no, folks.
You do not have to do the quotient rule. You're not doing the derivative of the whole thing. You're doing the derivative of the top, derivative at the bottom. Okay.
Okay.
Limit as x approaches 0. And I will show you how to do this without L'Hopital's rule. And then we'll use L'Hopital's rule. So first thing I do when I'm taking a limit, I plug in 0. And I get square root of 1 minus 0 minus 1 over 0, which is 0 over 0. Indeterminate limit. How you would have done this by hand in the past was rationalize the numerator. So I had this. So when I multiply out that top, the 1 plus x goes away. And the bottom, I'm just not going to distribute the x. So because it's conjugates, I can just square the first minus square of the second. That makes sense? The -1 times square root of 1 plus x and +1 times square root of 1 plus x cancel out. So those cancel. The x's cancel. And I get limit as x approaches 0 of 1 over square root of 1 plus x. One over 2. Now let's do it the L'Hopital's way of rule. L'Hopital's rule way. So that wasn't the worst algebra, but it's not particularly nice, is it? What? So it's never particularly nice? So now we're going to do the derivative of the top. I guess the -1 goes away. The derivative at the bottom becomes 1. Okay. Now I do limit as x approaches 0. The numerator is that, correct? The denominator is over 1, so I'm just not even going to write it. That was easier, wasn't it? This versus this. So let's do another one. So if I plug in, what's cosine of 0? 1. Think unit circle, cosine is the x coordinate.
So I was just trying
0 plus 0. So this is 0 over 0. Indeterminate. Let's use L'Hopital's rule. So we're going to take the derivative of the top. Derivative of 1 is 0. Derivative of negative cosine is sine. Derivative of the bottom is 1 plus 2x. Now when I plug in 0, sine of 0, the y coordinate is 0. 1 plus 0, and I get 0 over 1, which is 0. Is there another way that I could have done this? I think there's another way I could have done that, but it would have been harder. That wasn't particularly hard, was it? This next one would be particularly bad if I don't use L'Hopital's rule. I don't want to try to rationalize that numerator. Please no. So, if I plug in though, let's make sure. Always check that it is actually 0 over 0. Square root of 1 minus 1 is 0, so I'm left with 0 over 0. Okay, so I'll start with the derivative. Minus 1, x over 2 just is negative 1/2. This is 1/2. That's just over square root of 1. I still get 0 over 0 when I plug in. Okay. This would be 1 over 2 square root of 1 plus x. So when I plug in 0, I get 1 over 2 times square root of 1, which is just 1 minus 1/2 is 0. 2 times 0 is 0. The cool thing with L'Hopital's rule is you can just use it again. If this limit, my second one is still indeterminate, I can apply L'Hopital's rule until I get one that's not. And this is where I said Cadence's teacher made one up, and it took like 20 minutes, and I don't think he arrived at a solution. He just kept doing it. So now, 1/2 times negative 1/2 is negative 1/4. Subtract 1 from the exponent, negative 3/2. I don't need a chain rule because it's just 1. The negative 1/2 derivative goes to 0. The bottom goes to 2. Again, this is going to be 1 inside, so it doesn't really matter what the exponent is, right? So now I've got negative 1/4 over 2, which equals negative 1/4 times the reciprocal of 2, 1 over 2, or negative 1/8 is my limit. Okay? This isn't so horrible, is it? You're like, this really beats the alternative on limits.
Yeah.
I mostly agree. There, it can get kind of hard when we get to what we're coming up with. I'm going to do some other ones where things are approaching infinity. Limit as x approaches pi over 2 of secant of x over 1 plus tangent of x. Secant of x is the reciprocal of cosine. And it's going to infinity. Tangent also goes to infinity. Do you guys remember the graph of tangent looks like this? That asymptote is pi over 2. So you could also say, I believe cosine secant does this. So depending on which side, it's positive infinity or over positive infinity or negative infinity over negative infinity. The 1 does nothing for me. Infinity plus 1 is infinity. So I get indeterminate as infinity over infinity. Basically, we want to know, do these grow at the same rate towards infinity or different rates? Because x goes to infinity as you get large, but x squared and e to the x grow much faster to infinity, correct? So Noah, as you study programming, and I would assume this would show up in business, I know it shows up in programming, you'll have different rates of going to infinity. And when you write code, you want it to execute essentially as quickly as possible, right? So you have to learn about these growth rates because you'll have to think about it in recursive code. Okay. I'd assume there's applications like this in business too. So we've got indeterminate, let's use L'Hopital's rule. Derivative of secant is secant x tangent x. Derivative of my bottom is secant squared x. I can cancel one of those. And I get tangent x over secant x. Which if I just plug into this, will be indeterminate. But remember that tangent is sine over cosine, correct? Secant is 1 over cosine. So when I simplify these, I get sine of x.
Oh. Yay.
Yes, trig. I can plug in pi over 2 and say that's a y coordinate. That is 1.
No.
I'm picturing the unit circle in my head.
Like, it's the worst the trick get.
What?
Like, how bad is the trick get?
That's probably about as bad.
Okay, perfect.
It's not near, you're not gonna go. The trig identities in calculus, there's occasionally things that'll get bad, but most of the time they tell you what to do. Okay. We'll integrate, and there's some identities that are not exactly what we saw in, they're solved versions of what we saw in pre-calc, but they give you a hint. Switch it to this, use this identity. So you just switch it to what it tells you. You got to know some basic identities, but and it can go very far down the rabbit hole of identities, but not in calculus 1. Usually not in calculus 2. This next one is going to be kind of interesting, would be the way I would say it. So both of these, ln of x doesn't have an upper asymptote, right? It grows slowly towards infinity. Remember the graph looks like this, and it keeps growing. Square root also grows slowly towards infinity. So we get an infinity over infinity situation. But the question is, which one grows faster? So we'll use L'Hopital's rule. 1 over x. So I took the two derivatives. I will now multiply by the reciprocal of the denominator. And this is going to be an interesting use of exponent rules. That makes sense what I did?
Oh, yeah.
So now I can just add them together. So 1/2 minus 1 plus -1. I don't like to do the subtraction. I find it screws with me. So I usually just bring them up and add them. So ultimately, this is what I started with is equivalent to this by L'Hopital's rule. If I plug in infinity, that's 2 over square root of infinity is infinity. So apparently the square root grows faster than the logarithm, than the natural logarithm, and this will tend to 0. Does that make sense? Well, when you have a little bit of a puzzled look.
So, does the, oh, okay.
I did the derivative of the top over derivative of the bottom.
Yes.
And then I did a bunch of simplifying.
But why does that mean, how did you get to the conclusion that the square root grew faster?
So I'm looking at the original function. And I've got ln of x over square root of x. So I've got infinity over infinity. They both go to infinity. But this limit actually equals 0, is what I showed with L'Hopital's rule. Meaning, if any fraction goes to the 0, the denominator must be growing faster than the numerator. So my fraction, essentially, the further out I get, the fraction gets smaller. Like, say 1 over x, as I get large, goes to 0 because x gets large, right?
Yeah.
Or x squared over x cubed grows faster than x squared. So when I divide them, this will go to 0. So my conclusion, if this goes to 0, my denominator must be larger as I get big than my numerator. Meaning my denominator must be growing faster than my numerator. That kind of makes sense?
Yeah. Maybe it's grow, you did with the Xbox. Yeah.
What?
It could be a grow. It's at the end there.
Yeah, I have a lot of experience, so I can kind of just do them. And yeah, it's gonna take a second to like, oh yeah. It's funny, we often say the calculus is easier than the algebra in calculus. You're like, these derivatives weren't that bad. Oh, but simplifying, or the algebra was easier than the trig. Or the calculus part was easier than the trig. Okay. Here is a really interesting trick.
So what is it?
So here, if I plug in sine x goes to infinity times sine of 1 over x. 1 over infinity is going to 0, right? Sine of 0 is 0. So I get infinity times 0. But neither one of these is actually infinity or actually 0. It's just getting really close, right?
Right.
So is the infinity larger than the thing is small? Is the big larger than the small, or the small larger than the big? Or are they in some ratio to each other?
Assume they're in some ratio.
Yeah, it's 1. The limit here actually equals 1. So we're going to use a little trick. H here equals 1 over x. Okay? So as x goes to infinity, h would be going to 0, correct? So I'm going to change my limit from x goes to infinity to h goes to 0. X would then be 1 over h, correct? I'd just solve this. Which could be thought of as sine h over h, which that was a known limit of 1. Or you can show it via L'Hopital's rule. Derivative of sine is cosine. Derivative of h is 1. Cosine of 0 was 1. So L'Hopital's rule makes this one that I think I worked out with a bunch of trig identities. Well, actually, I don't think I think you guys would. We'll just believe it. But it's about 10 minutes worth of trig identities to work that out.
I believe it.
But via L'Hopital's rule was 10 seconds. One more, and then you get to practice. This worksheet does not get nearly as hard as the book. The difficulty in this book is more for Calc 2. Okay. And you may or may not do that in Calc 2. Calc 2 varies a little bit place to place. If we get time, I'll show you integration by parts. It's not as bad as it, you just have to be careful. So our last one, limit as x approaches 1. And when I plug this in, ln of 1 is 0. 1 minus 1 is also 0. So this is 1 over 0 minus 1 over 0. Hmm. That's not allowed, yeah. So before we apply L'Hopital's rule, we're going to find a common denominator.
You got it.
Which means I'll multiply the left by x minus 1 and the right by ln x. And I cannot cancel these x minus 1s because of that minus. Okay? Do not accidentally do that. It doesn't work. So now let's do the derivative. This is not as nice of a derivative. Derivative of x is just 1. Derivative of 1 is 0. Derivative of ln x is 1 over x. Derivative of the denominator, x minus 1. This is a product rule. Plus 1 ln x. I think I can do this. 1 minus 1 over 1 over 1 minus 1 times 1 over 1 plus 0. Darn it, that's still 0 over 0. So we're going to have to do some algebra on this. I don't want to yet. Because I got a product rule down here. This isn't. So I'm going to get a common denominator up here by multiplying this by x over x and that by x over x. So I'm going to get common denominator on the top and the bottom. So I'm going to make those a single one because they're now the same. I don't need that anymore. So now I multiply by the reciprocal. Now I at least don't have fractions and fractions. because those x's cancel.
No. No.
So I'm still looking at limit as x approaches 1. Now I'm going to take the derivative again. 1 on the top, 1 plus x times 1 over x. Now I'm using the product rule on the x ln x plus 1 ln x. X times 1 over x is 1. That one's kind of hard.
Oh, silly, yeah.
I was like, they got a lot harder towards the end, but a lot of them you'll get to do like the beginning ones. Okay? That is L'Hopital's rule.
Mhm.